All right, so this is the technical walkthrough of the artifact rejection and the signal processing that we've covered so far in modules 1 and 2. So this is what's called Jupyter Notebook. The actual link to this notebook will be available on our GitHub, which I will link in the description below. So if you're not familiar with Jupyter Notebooks and how exactly it works, we have some instructions on how to install it, which you can follow here. But to just give you a brief orientation of what it's all about, the Jupyter Notebook is different from an IDE in terms of programming because a Jupyter Notebook has these individual things that we call cells. And you can enter segments of code in this cell and build upon it in subsequent cells. What's unique about Jupyter Notebooks is that you can run each cell individually. And this is especially helpful when you're trying to plot data like so, because you can directly write a line of code and see its corresponding plot without having to write a bunch of lines of code and have them all populate in one single go. So it's very iterative. You can walk through it. You can annotate and comment exactly what you're trying to do. It makes for a very readable, very easy to follow case study sort of format for code, which is really nice. So once you take a look at this notebook and once you follow all of these instructions, you'll basically have your first cell open for you. And the first thing we do is we say import MNE. MNE is a signal processing library for brain data specifically. It allows us to do EEG data, EMG data, MEG data. They have all sorts of nice handy functions that are easy to use that we would commonly use when interpreting any sort of physiological signal. So the first step that we do is import MNE, and MNE has their own data sets that are available to experiment with. So for the sake of this demonstration, we just use one of their data sets instead of one of our own. And so we basically get the path of the data, which you can see is populated over here. And what we do is we append that to exactly what we're trying to pull out of there. And we say mne.io.read, and we pass in the path. So this function is part of MNE, and we pass in the path where it's exactly stored on our machine, which will be different for each person. And we store that in the variable raw. After we've done that, we can basically say raw.info.get. And nchan is a parameter we pass in, which allows us to get the number of channels. This is just useful in knowing what kind of data you're working with and how big is it? How many channels are we dealing with? EEG data can range from 8 channels to 64 to 128. And in this case, we have 316. So let's look at the raw data and see what it looks like. So we do a very simple call. It's raw.plot, and it'll plot all the channels. Actually, it won't plot all the channels. You can see it's only plotted some of them. And you can see what the data looks like. So this is pretty typical of what we expect. EEG data isn't much to look at when you look at it raw like this. There isn't much you can decipher. And it's a good thing if nothing stands out in particular, because that means there isn't a whole lot of noise or there isn't anything that is glaringly wrong with this. Obviously, some channels here are more noisy than others, but that's what the whole processing tutorial is for. So you have the raw channels that are being outputted. MNE does this weird thing where it outputs the same plot twice. So you can see that this is no different from this plot. It just likes to do it twice. Why? I'm not exactly sure, but I've had the same experience as well when I plot my things on Jupyter Notebook too. So once you plot the data, this is just for you to explore and see okay, this is what the raw data looks like. There's another format for storing EEG data, which is EDF files. And so this is another way to take a data set from MNE. And instead of over here, we did read raw fifth, which is the file that we stored, format that we stored in the first time. You can do read raw EDF. And so cells 5, or this cell and this cell are basically doing the same thing as before. They're taking another data set from a different format and reading it. And you can see here it's printing out a bunch of confirmation that it is being read. And if there are any issues, in this case it says could not determine channel type of the following channels, they will be set as an EEG. And so sometimes the data file that you pass in does not have all the fields filled out, so it's not explicitly spelled out. What file this is actually is dependent on MNE, but we're using one of their data sets, so there might be some issue with that. And that's why it's saying these things. And you can plot the raw data here. Here you'll see the raw data looks quite different from the data over here. I think it's just a matter of colors and how squished it is. You can obviously, like if you're trying to specify the way you're trying to plot it, you can elongate it and make sure it's not all jumbled up so you can see it more clearly, just like you can see this. But those are just to tell you that, there are different file formats, and, plotting it will, and the functions should more or less be the same, but there are different formats. So it depends on what you are working with. So the next step, is referencing and artifact rejection. So a common step for EEG data specifically is you want to have a reference electrode. And we covered that more in module 1 about why you need a reference electrode and what is the point of a reference electrode. But oftentimes there are 2 ways to do referencing. Referencing can be done online, which means while the data is being collected, it is also simultaneously being referenced. Or referencing can be done offline, where we've collected all the data, even the data from the reference electrodes, but after the data has been collected, you manually go back and reference the data relative to the reference electrode. So here we're saying, raw.set EEG reference. And if you had a reference electrode, you would pass that in as which one you wanted to set as a reference. But if you leave it blank, it'll take the average of everything and use that as a reference. So it averages out all the electrodes for every single time point. Excuse me, it averages out all the electrodes for every single time point, and then it uses that as a reference for everything going forward. So we do that. The next step is just to look at what the PSD spectrum looks like. So we covered what a PSD plot is. And again, you see a similar type of plot happening. So you have frequency from 0 to 80 hertz, and you have the magnitude on the Y scale. You see that all frequencies are present at every single frequency is present. The extent to which it's present, the magnitude, is what we are after. Something you'll notice over here is that, again, at 60 hertz, we have a peak higher than any other peak in this graph. And like I said earlier in the previous video, depending on which geographic location you're recording your data at, the electrical devices, the frequency at which the electrical devices are in that particular location could impact, could be seen on the PSD and could show up as a feature. So we're probably in the US, when this data set was recorded, and devices in the US operate at 60 hertz. So any other electrical devices in the vicinity of the EEG data collection system will be picked up. And that's why we would need to implement a notch filter to get rid of this 60 hertz that we see over here. Again, MNE just plots things twice, and I'm not sure why it does that. But moving on, so here's a raw plot. Let's see what it looks like after we filter. So filtering in using MNE is very simple. It's literally raw.filter, and you pass in what frequencies are trying to filter out. In this case, we passed in 0.5 to 30, and we basically wanted to set up a bandpass filter from 0.5 to 30 hertz. So if you remember, a bandpass filter basically allows frequencies to pass within a given interval. So we're trying to select frequencies from 0.5 to 30 hertz. And let's look at what it looks like after it's been filtered. So we see that we have 2 vertical lines, our 2 cutoff points, 0.5 and 30. And the frequency in this graph, or the PSD plot in this graph, should be relatively same as the PSD plot that we see over here. So we see that it starts kind of at 20 and goes down to a little bit below 0 by the time it hits 30 hertz. Over here also, we see that it starts around 20 and goes a little bit below 0 around 30 hertz as well. It does start a little higher over here, but we've also started filtering out at 0.5, so that part has probably been cut off earlier. As for the rest of the graph, we see a gradual phase out up to about 38 hertz, and then it almost kind of dampens. It's completely mute, completely flat, not a high power across all of these frequencies. So The PSD plot is a great way to see whether your filter actually did what you asked it to do and whether it's matching up with the code that you wrote. And so this is, a very short tutorial. It's not too intensive, but hopefully this illustrates how you can take these signal processing techniques you learned in the previous video and how you can actually apply them in code and what it looks like using Python and some basic functions that MNU gives you. So I hope that was useful.